let me introduce Professor Oleh Yermakov from Karazin Kharkov National University, and his talk entitled Discovery of Polarization, Degree of Freedom for Localized Light. So, Professor Oleh, please continue.
Thank you. This work was done in collaboration with Sergei Polevoy from Uskov Institute of Radiophysics and Electronics in Kharkiv. And I will divide it in two parts, I think. So let me start from the very beginning. What are the plane waves in electromagnetics, in optics, in radiophysics? This is just, it can be expressed by the following formula, where we have some complex amplitude E0 and the phase factor, which is written in the degree of the exponent. And let's imagine that the wave propagates in some, for instance, in the plane of the screen, and the wave vector have only two components. Then, of course, I will write the Maxwell equations. All electromagnetic tasks, optical tasks are started from Maxwell equations. I will write two equations for the curve. So this is two vectorial equations, which gives me 6 scalar equations. And surprisingly, if I will solve them, I can divide these 6 resulting equations into 2 groups from 3 equations. And you can see that each group contains only specific components of electromagnetic fields. And they're defined by the polarization of wave. So a plane wave can have, in this sense, either TE polarization, which means transverse electric. So so electric field is perpendicular to the propagation plane, perpendicular to the XZ in this case, or vice versa situation when magnetic field is transverse. This is called TE and TM polarization. So this is the fundamental polarizations coming directly, explicitly from the Maxwell's equations. This is the basics. But surprisingly, both these polarizations have the same dispersion law. So by solving any of these two system of equations, I will obtain the same dependence of the wave vector on the frequency. And this is just the linear dependence. If I put on the graph, they will be the same in the vacuum and in any homogeneous isotropic space. This is just a reminder of basics of electromagnetics. So what we have then? Any bulk medium, homogeneous isotropic medium, the spectrum of the bulk medium is double degenerate with respect to polarization. And it allows to change the polarization of light very flexibly and very easy. We just need to break this polarization degeneracy by introducing some anisotropy. Usually it is done by uniaxial crystal. These two lines are splitting, and we have some fast delay, so we can change the polarization on demand. It's very easy. This is a basic fundamental principle of any polarizing device, of any polarizer. But from other hand, in the modern era of miniaturization and polarization, one needs to manipulate light and electromagnetic waves almost into dimensional space. So we need to play with localized light. In this sense, we should go under the light line in this region. And the simplest example of such a system is just a dielectric slab waveguide. So this is just the dielectric slab of finite thickness. In this case, you can see that eigenmodes are under the light line. So it means that the wave vector are much higher than in the vacuum, in the homogeneous bulk space. And it means that, that the wave is highly localized. It's called guided waves, for instance. But you can also see that polarization degeneracy is broken in this case. So we obtained the highly localized waves but we lose this polarization degree of freedom. Now we cannot manipulate the polarization of these well-localized waves. And this is, of course, the problem. So it means that when we go to the miniaturized devices, we lose the polarization degree of freedom. And what is the polarization? This is amount of information. Linear polarization, elliptical polarization, circular polarization. This is some analog of optical bit of information. Yeah, and we lose it. This is very bad. And what we propose here, this is to introduce the system where the spectrum of eigenmodes are simultaneously both well localized and at the same time degenerate. So it means that we bring polarization degree of freedom for highly localized light. And in the simplest approximation, it can be achieved by structuring this dielectric slab waveguide. But I will use the terminologies. We will create some all-dielectric metasurface. So to say, periodic array of subwavelengths all-dielectric particles, which and its spectrum of this metasurface will be something like this. Why and how we will do it? So the concept is based on the Mie resonances. If you will take the sphere with high index done from high index material, it was shown that such a sphere has both electric and magnetic resonances, so electric and magnetic responses. Even more, if the sphere have the enough weak radius, we can decompose its response coming from electric dipole, magnetic dipole, electric quadrupole, magnetic quadrupole, and higher orders multiples. And it was shown, it's called sometimes magnetic light, and the first works in this direction arise in 2012. So here you can see the dark field spectroscopy from silicon spheres of different radius. And what's interesting is that the interplay between effective electric and magnetic responses, polarizabilities or whatever. So we can achieve, for instance, zero backward scattering, zero forward scattering, something like this. And we would like to do the same, like Huygens principle-based game, but in the near field. It hasn't been done. I skip the analytical model, numerical model, and come to the results. So our metasurface represents a periodic array of such a dielectric cylinders packed in a square array. Yeah, and the dispersion, the dependence of frequency on the wave vectors looks like this. So we can see the TE and TM mode are degenerate, and the fields are orthogonal. The fields of each eigenmodes are orthogonal and can be characterized as TE and TM modes. When I say that they degenerate, I'm not completely honest with you, because indeed we engineer them to be very close to each other. So it is not the degeneracy like in quantum mechanics. Indeed, this is just the dispersion engineering. And we evaluate how close they are by introducing some polarization degeneracy degree. For instance, we fix the frequency and calculate the difference in wave vectors between two modes at the same frequency. Yeah, and we can analyze these values, so you can see that this polarization degeneracy degree doesn't exceed 10 to minus 3 in the pi over a units. Practically, it means that electromagnetic wave can propagate along hundreds of periods with negligible phase delay, and this is more than enough for practical applications. And another idea is to do some kind of one-dimensional waveguide consisting of a chain of cylinders. So in this case, it's also possible to achieve this polarization generate spectrum dispersion. And even more, using some MPP package developed by MIT team, we can quickly calculate the proper design for the specific pre-selected applications. So we can find the design for the specified polarization degeneracy degree and localization degree. For instance, we need some design of metasurface with polarization degeneracy. No, it's here 10 to minus 3, and localization degree, which is defined as the ratio of the vectors 1.2. This is this design. And we also make the dependence of the ratio of cylinders sizes on the permittivity. So in principle, it can be done for any material. We need to fulfill on the two conditions: big dispersion in the needed frequency range, and big dispersion. Maybe that's all. So it can be done for different materials in different frequency ranges. In order to verify this concept, we made the following experiment in microwaves, where it's more easy. Just to start, so we make such a chain of ceramic cylinders. Ceramic is high-index material in microwave spectrum. The permittivity is around 40, something like this, 42, 44. And we use such a loop with current, which acts like a vertical magnetic dipole to excite the eigenmode, and the same loop to scan the field. And this loop moves along the structure, measure fields perpendicular component of magnetic field in different points, and we can recover the map, special map of the electromagnetic field. And applying the two-dimensional fast Fourier transformation, we can extract the dispersions from the field, special distribution of the fields. And here you can see the dispersions simulated numerically and extracted from the field measurements, experimental field measurements for TE and TM modes. And we put them on the same graph, and you can see that they're pretty similar, and the level of polarization degeneracy degree are also the same. So we have a good coincidence between numerical simulation and the experiment, and indeed this concept works. And what then? Then we, of course, would like to propose some of multiple possible devices using this polarization degree of freedom. The simplest example, this is a planar polarizer of guided light. So how the conventional quarter wave plate works? You have the linear diagonal polarization at the input. Then you have uniaxial crystal, which gives you some fast delay delta k, and you take the length of this uniaxial crystal in such a case to obtain pi/2 fast delay. And then the output you have circularly polarized light. We propose to do absolutely the same idea, but in two-dimensional system using this metasurface with polarization degenerate spectrum. So this metasurface plays a role of vacuum, and some modified metasurface plays the role of uniaxial crystal of anisotropic medium to split these curves to induce the fast delay. Yeah, so this is the idea. We took this chain of cylinders and put some other cylinders in the center. So this is the idea. And the experimental setup was also the same. So we use excitation loop from one side and measure the the field distribution here before the polarizer and here after the polarizer. Here we are working in the formalism of Stokes parameters and Poincare sphere. In simple words, any point, the sphere covers all possible polarization states, the surface of the sphere. And we change the polarization from such a polarization state to this polarization state, for instance. Here are the results of numerical and experimental measurements. So we measure the field distributions in these cross sections before and after polarizer, and you can see that in you can even forget about the colors and Stokes parameters and look at the black figures corresponding to the instantaneous polarizations in these points. And we had linear diagonal polarizations before, and we obtain circular polarization after the polarizer in numerical simulation. In the experiment, we were not successful to excite the linear diagonal polarization. And you can see that indeed we excite such an elliptical, elongated polarization, and the axis of this ellipse is also along the diagonal. You can see that these ellipses are rotated by 90 degrees. So despite we did not excite the needed polarization, we can see that retardation is still pi/2 here. It was the first part, but there is another option how to change the polarization of localized waves. And it is based on very old concept, which is called Babine principle. It is described in any optical books. So the idea is the following: if you have the hole in the metallic screen, you will obtain some diffraction picture, right? But if you will now take the complementary part, so the metallic pattern exactly corresponding to this hole, we will obtain another diffraction picture, and these two diffraction pictures are strongly connected to each other. This is the idea. So you can see some self-complementary pattern from the real world, and we take the metasurface based on this principle. It consists of a periodic array of inductive and capacitive lines. In reality, it may look like this. This is our real sample, and this like complicated pattern also gives us the multiple resonances. Of course, this is, you can see this is an isotropic system, two-dimensional system, so it may be described by two-dimensional tensor, anisotropic tensor, of course. And the main focus is that the properties of this metasurface are exactly described by the following principle. So here, why this admittance? This is something like surface analog of conductivity in microwaves. So in simple words, this is surface conductivity along x and along y directions. And they are constant at any frequency because y0, this is an inverse surface impedance in vacuum. So this is constant. So determinant of this tensor is constant. This is describes the properties of this so-called self-complementary metasurface. And we study surface waves at these self-complementary metasurfaces. And such a simple principle gives amazing results. So here you can see the dispersions of TE and TM surface waves at any two-dimensional systems. So they are typically different along x, along y directions, along any direction. They can accidentally intersect in some points, but it works only at single frequency. And here we have the dispersion for self-complementary metasurface along the main axis, along x and y axis. And they're absolutely the same. And here, this is not dispersion engineering. They are totally degenerate, like in quantum mechanics. This is the direct consequence of Babinet's duality principle applied to two-dimensional space, to metasurfaces. Yeah, and we can, of course, derive the exact analytical expressions for the dispersions of TE and TM surface waves at self-complementary metasurface. Moreover, another interesting property of self-complementary metasurface is shown here. This is the K-space, the frequency contours, so the contours of the eigenmodes in the same frequency. And such a flat isofrequency contours, which you can see here, are called correspond to the canalization regime. So it means the ultra squeezed propagation of surface waves along one direction. It's used for imaging, etc. And again, while we have for any conventional two-dimensional system, in the best case, something like this, so they are not completely flat. Here we call this region extreme canalization because the lines are absolutely flat, and this is the consequence of the total correspondence between poles and zeros of the perpendicular components of surface conductivity tensor, which is caused by Babinet's duality principle again. So to check these results, we also made the microwave experiment. The idea is the same. We use some probe a loop exciting TE and TM modes, acting as vertical magnetic or electric dipoles, and the same elements to measure the fields. And we obtain these different field profiles. You can see here hyperbolic light profiles, and here there are horizontal canalization, vertical canalization, again horizontal canalization. So you can see that here we have the propagation in one direction, which is useful for antenna application, etc., where you need to transfer the signal from point to point with no energy loss. And we extract the dispersion from these fields, and you can see that they are pretty close to each other, so supporting our theoretical investigations. And in the most interesting case, we can achieve both polarization degeneracy and canalization region, which means that we can transfer the energy from the source to receiver by saving the initial polarization state. For localized light, it hasn't been done before. And finally, the last part, we use this idea to manipulate the polarization of surface waves. So now we know that TE and TM modes are degenerate, and we use port, put it in this metallic part, and port 2 located here in the complementary part, and port 1 excites TE mode, port 2 excites TM mode. And then we can check it here that if we switch on only port number 1, we obtain horizontal polarization. If only port number 2, vertical polarization. And that's all what we need. We started from Maxwell equations. Then if we will add these two polarizations with different complex numbers, we can obtain any polarization. And that's what we do. So manipulating amplitudes and phases at each port, we can achieve any polarizations on demand. For instance, we show the linear diagonal polarization or circular right and left handed polarizations, or any polarizations on demand covering any point in this Poincare field. For instance, here we do such a elliptical polarization. Here we use some periodic boundary conditions, but we have also checked it for the finite size system. Yeah, we took 10 ports to excite the surface waves propagating in the void of Fourier period and exciting the needed polarization state in such a region, such a finite width region. I think that's all. And just to conclude, so we propose two concepts. First is based on the mirror resonances in all the electric metasurfaces. Second is based on the self-complementary metasurfaces based on the Babin duality principle. And in both cases, we achieve polarization degeneracy of localized eigenmodes, which allows us to obtain polarization of localized light on demand to change the polarization state of propagating localized light at the same frequency. And it discovers huge opportunities for applications. Thank you for your attention. I would like to thank the Armed Forces of Ukraine for the service, which allows us to conduct the research in this time, in these difficult times. Thank you.
Thank you very much for very inspiring talk. So let us open the discussion. So do you have any questions in regards to the given presentation? Yeah, I mean, maybe I will have a first question. So this was already discussed partly by us, but let's say you have coexistence of you have a certain degeneracy between TE and TM modes, right?
Yes.
And to what extent you can make benefit of that, and to what extent it's obstacle for certain applications?
So the range of applications covers by the frequency range, I think, where we have the degeneracy. So for instance, here in this region, we have good degeneracy, but it's not very interesting because the eigenmodes are close to the light line. So it is almost the same as we are working in vacuum, where we can play with polarization very easily. So it's not very interesting. So here's the interesting case, of course, is this region where the waves are well localized. And it is not so wide for this specific design, for this specific case. It is not so wide. And we are always interplay between degree of localization and degree of polarization degeneracy. For more localized light, the degeneracy is not so good, and of course it limits the possible applications. So this is the first point. Second point, I think that all classical optics, which we need to transfer to the 2 dimensions, to the planar photonic and optical devices, should be able to should be adjusted by the polarization. And here, why we do it. So this is a platform for new generation of planar polarization devices. I have shown only one clear application. I think this is this planar waveguide polarizer. So you can change the polarization of the propagating guided waves at the same frequency, which has not been done before. But indeed, the range of application is huge. One of the not trivial ideas is to use it for chiral sensing, for instance, because chiral molecules are polarization sensitive, and we need high localization to obtain the the good response measurements here. This is sensing part, but chiral part here lies in the polarization, and I'm pretty sure that this polarization degenerate spectrum will greatly boost the sensitivity of chiral substances, for instance. the answer.
Yeah, thanks. Just a question. So how small signals you can tackle? You cannot deal with single photons, right? You have to be much above that.
Yeah. It's not about single photons. Yeah, here we are. I don't know. So of course here we are working with the packets, yeah, of photons with the waves, but I don't see the limitations in this formalism.
Yeah, I just wonder if you put your signal down to one photon, does the whole results are a bit similar, or it's like
good question. So I think if we have one, I don't know how to answer here, so we should think about it. But I think that for one photon, it means that of course we can specify the polarization of this photon on demand, but we can do it without this stuff, right? But I think that if we have two photons, it will be more interesting, because here we can set the intended state. Yeah, this polarization. So the entanglement of those two photons may be adjusted.
Right. I mean, I'm asking because there's some companies in Netherlands that already produce photonic processor that works at room temperatures, and they are able to entangle 17 photons at the same chip. And yeah, I mean, I rather deal with superconductivity, so this optics is not my field, but it was just a kind of open question how things are in that way. But anyway, probably it's still a kind of open question how things behave if we downscale the signal, right?
Well, yeah, I didn't think question.